Hi, I'm Richard, and I'm a retired engineer. I have often thought about things like magnetism and gravity, but none of the explanations I have seen really satisfied me. A little while ago, I started to concentrate more on the fields themselves, not the underlying mass or the magnet. I have already made a video describing how I think gravity works and explained it in a way that most people can understand quite easily. That video is called Gravity, How It Works Intuitively. In this video, I will describe how exactly magnets move things in a way that the average person can understand. To help in my investigation of magnets, I purchased a Gauss meter. Now I can detail the flux density of various magnets and map out the magnetic field. So let's get started. Okay, let's do a little bit of history. In 1820, Ørsted, a Danish scientist, discovered that current in a wire creates a magnetic field around the wire. Now, people knew about magnetism because way back in antiquity and beyond, people had discovered lodestones, which are magnetized stones. Lodestones are made of magnetite, an oxide or ore of iron. It's believed that these lodestones got magnetized when a strong lightning strike created enough current to form a strong magnetic field which magnetized the magnetite. It's always a current, a moving charge, which causes magnetism. They go together. A moving charge creates a magnetic field. A moving magnetic field creates a moving charge. That is electromagnetism. Let's talk about how some different kinds of magnetic fields are generated. The simplest, as we see here in the drawing, is an electromagnet. This is easily created by taking a piece of iron rod and wrapping a wire around it, putting a current through that wire. As you can see in the drawing, a magnetic field appears around the conductor, and when the conductor turns are wound tightly together, the magnetic fields all join together to increase the magnetic field in the iron rod. Now, we also know that the Earth has a magnetic field. In this case, of course, the Earth is turning every day, and it's a big world out there, and so there is enough moving charge in the Earth to create a magnetic field between the North and South Pole, or the axis of rotation of the Earth. It's a small magnetic field which can be measured fairly easily, but it can be overcome by other magnets pretty readily. Another interesting thing about that is that the sun and black holes both have very large magnetic fields, and both the sun and black holes are spinning. What doesn't have a magnetic field is the moon. The moon is really not spinning, or at least not spinning very fast. It's only turning once every 28 days. So no magnetic field is generated. The strength of a magnetic field is measured in flux and or flux density, which is a flux per unit area. Flux density units are Gauss or Teslas. 1 Tesla equals 10,000 Gauss. 1 millitesla equals 10 Gauss. A small rare earth magnet has a flux density at its face of about 400 millitesla. A small iron magnet has a flux density at its face of about 40 millitesla. The Earth's average value of its flux density is 0.03 millitesla. The pulling power of a magnet is proportional to the flux at the face of the magnet. What I'm going to demonstrate here is how a magnetic field is like a spring under tension. So for starters, here's a real spring with a weight attached. We now have a system under tension. So there's a force pushing down and a force from the spring pulling up. Right now, they're equal forces and nothing is moving. But it is an extreme tension. If I were to disturb this a little bit, we now have a system oscillating at its resonant frequency because of the tension in the spring. What I'm going to do next is show you something very similar using just a magnetic field. Now I'm going to demonstrate how the magnetic field is in high tension and can act like a spring. I have a strong magnet protected by styrofoam to protect it from damage if it gets hit. I have a coiled wire attached to an oscilloscope to measure the change in the magnetic field. And I'm going to take this other magnet and dangle it by a string and give it a little twist. And you can see that it's oscillating. And it continues to oscillate back and forth, with the magnetic field acting as a spring. This could go on forever, I think. I'm going to have to stop. And here's what the probe is picking up as the magnet oscillates. Here is that strong magnet again, this time with a compass, which will continue to oscillate for quite a while because of the springy nature of the magnetic field. Here I will show you what happens when we start adding magnets together in series. And this will vary, of course, a little bit depending on the type of magnets used. As you can see, we have one magnet with 25 millitorr, two magnets stacked is 60 millitorr, approximately double, three stacked is 97 millitorr, approximately 3 times. When additional magnets are added, a smaller increase occurs because the material reaches its saturation point. Here is a stack of 4 disc magnets with thin spaces between the magnets, with just enough room to insert the Gauss meter probe. Both ends have 86 millitorr pulling away from the stack, but almost double that between each magnet. The net force is holding the stack together. Here's a drawing of a small bar magnet, and I've sketched out the external magnetic field around the magnet. I've also shown in a couple of places what I measured the field density at various places. These values are in millitesla. The red areas behave like a north pole, while the blue areas behave like a south pole. There are 2 types of vectors in the drawing. The first vector is the white arrows, which basically traces out the force lines in the magnet and the external magnetic field. By convention, the field lines go from the north face to the south face through the external magnetic field. The field is also inside the magnet and runs through the magnet from the south to the north. With respect to magnets, all materials have a permeability value, which is the ability to hold or conduct a magnetic field. And by definition, the permeability of a vacuum equals 1. The permeability of iron is greater than 5,000. Therefore, a magnetic material can conduct a large magnetic flux in a small space, while in a vacuum, a large space is needed to conduct the field. The magnetic flux flows in a loop from the south to the north inside the magnet and from the north to the south outside of the magnet. The force a magnet can have is directly proportional to the amount of flux coming out of the magnet. The black arrows in the drawings are the force vectors. With a magnet in equilibrium, the flux density at the south pole equals the flux density at the north pole. So the north and south face of the magnet are pulling towards each other equally through the external magnetic field. The forces cancel out and nothing moves. It's an equilibrium. Now let's get down to how these things actually work and move things around. As we can see, In this picture, the two magnets A and B are far enough apart so their respective magnetic fields are not interfering with each other. When we measure the flux at the North Pole and the flux at the South Pole, we find both are equal to each other, and the forces on the North and South Pole are equal and therefore cancel each other out. Now we look what happens when we bring the North Pole of magnet B up to the South Pole of magnet A, and we get within range so that their magnetic fields interfere with each other. First of all, we notice that the flux direction of magnet A is the same as magnet B. When we measure the flux at the North Pole of the magnet A, we notice that it is now no longer equal to the flux at the South Pole of magnet A. In fact, the flux at the South Pole is much higher than the flux at the North Pole. These magnets are no longer in equilibrium, and they're going to try to get back into equilibrium. And when we look at those values of the flux, and again note that the force is directly proportional to the flux, it means that the vector of force at the South Pole is much greater than the vector of force at the North Pole. And therefore, we subtract one from the other, and there's a net force that is pointing in the direction of magnet B. And therefore, the net force will bring the magnet physically towards magnet B. Now, what happens when we actually take one of the magnets, B, and flip it around so that the two south poles are now facing each other? Again, I measure the flux at the North and South Pole of magnet A. And now we come to find out that actually the flux at the North Pole is higher than the flux at the South Pole. And therefore, the force on the North Pole is higher than the force on the South Pole. And now, therefore, the net force on the magnet is pushing it away from magnet B. So that is easy to understand. When the flux is higher between the two magnets, it's going to force the magnets together. When the flux is lower between the two magnets, it's going to force them apart. So that's pretty much how it works. It is the force vectors on the two poles which determine which way the magnet is going to move. Some may say that a magnet attracts iron and steel objects. It does, but only after the iron or steel get magnetized. Here's a nail. I've just taken it from the box. I dip it into some iron filings, and we do get a couple of filings sticking to the nail. Now I'm going to hold the nail down. I'm going to bring one of my magnets to about an inch away from the nail. Okay, it's not touching the magnet, but it's probably is within the field of the magnet. I'm going to take the magnet away. Let's see what happens now when I dip it into the iron filings. Okay, there are a lot more iron filings on the nail now, as you can see as they come off. Because as soon as the nail gets close to the field, it becomes magnetized. And at that point, its magnetic field will react with any other magnetic field and get drawn in. So that's how a magnet attracts all magnetic materials, because all magnetic materials will become magnets when they get close to a magnetic field. So there it is. A magnet has a force vector at the north and south poles. The force vectors will be equal in an undisturbed field. When disturbed by an external magnetic field, the force vectors will no longer be equal, and the magnet will move in the direction of the stronger force. I hope I have explained magnetism and made it less mysterious. Thanks for watching.